Hello students. In the earlier lecture, we discussed the definitions of the cross sections and we learned how to transform it from the lab to the CM frame. In the conclusion, we reached that is applied to the classical as well as to the quantum mechanics. In today's lecture, we are dealing with the quantum description of the scattering. For simplicity, we consider the case of the two spinless and non-relativistic particles which has masses m1 and m2, and we assume that the scattering is between the two particles is elastic scattering. Here we assume that the particles are non-relativistic. This is because that whenever we are dealing with the scattering of particles, the particles are non-relativistic. If that means that their velocities will be less than that of the c, speed of light. So because if the particles are moving with very high speed, which is relative to the speed of light, then the quantum mechanics doesn't deal with that. For that case, the relativistic quantum mechanics is used, and the equation used for those particles are the Dirac equation. And also we consider that the particles are spinless, so there is no spin considered in the particles. So the case is, we are in this situation we are keeping the case simpler. Also we assume that the scattering is elastic scattering. That means that, for instance, I will explain it like for example, the wave vector of the particle before the scattering and after scattering, that is the same. For example, if before the scattering the wave vector of the incident particle was, let's suppose, k0, and after scattering the wave vector of the particle is, let's suppose, k, so their magnitude will be same. So such a scattering is called elastic scattering. Also, the frame which we are using will be the center of mass frame. That means that I will write these points here, that the particles are non-relativistic, second they are spinless, and that is the frame is center of mass frame. So these are the assumptions which we are taking in account, and also we assume that the interaction potential between the particles is time independent. That is the I will write it here, and the interaction potential between the particles, that is the incident particle and the target particle, is time independent. That means that this V R1 R2 is time independent. And for which we know that the time independent Schrodinger equation is used. That is the time independent Schrodinger equation for this case will be minus h cut square upon 2 m1 del 1 square minus, this is for the first particle, and this is minus h cut square upon 2 m2 del 2 square plus v r1 and r2 psi of r1 and r2, which is equal to E psi. And this is the total energy. This is equation number 1. Here because we considering the case of two particles, this is the incident particle, its mass is m1, and here is we have a target particle whose mass is m2, and let this particle is allowed to interact with the target particle, and after interaction it scatters with an angle theta in this direction. Here this is the potential between these two particles, and now this is a two body problem. This is a two body problem, and we are using the center of mass frame, and we know that we can replace the two body problem, we can transform from two body problem to the one body problem by assuming a fictitious particle which is called reduced mass. That is, we are using that mu is, it is the reduced mass m1 m2 upon m1 plus m2, and which is moving through this potential, which moves in the potential v of r. And now the Schrodinger equation for this particle, the reduced mass, is minus h cut square upon 2 mu del square psi of r. So there is the wave function is now it is independent, time independent wave function, so we can write it as psi of r. So it is not necessary to write it as psi of r1 and r2 plus v of r psi of r, which is equal to E psi. This is equation number 2. Now the problem of scattering between two particles is thus reduced to solving this equation. So it doesn't need to solve this equation for the solving scattering problem, so we have to solve this equation for the scattering of two particles. So our job is to show that differential cross section in the CM frame can be obtained from the asymptotic form of this equation. It means that first, if we solve this equation, this Schrodinger equation for psi, and after applying some limiting conditions, and after that limiting conditions which we obtain, that will be the solution of the this equation, and which will be used for the calculation of differential cross section in the CM frame. That means that it will give us the probability of number of particles scattered, in the direction of theta and phi through the solid angle d omega. So after solving this equation for psi and applying the asymptotic limits to that equation, which will give us the differential cross section or the probability of number of particles scattered in the direction of theta and phi through the solid angle d omega. So to explain this phenomena through quantum mechanics, this is the target particle, and in quantum mechanics we consider the particle to be a potential. Let this is a region of some potential which has some potential v of r, and this v of r has a finite range. Let this region is, let's suppose, A. So it has a finite range. That means that this v exist in a region of r less than or equal to A. Beyond that the potential is 0 and the incident particle passing through this region will be a free particle, and that this is a incident particle which is approaching toward the target or this potential region. So let here the incident particle, and in quantum mechanics the incident particle we usually represent by plane waves. So it is a plane waves, and this is traveling along the z-axis. So this is the z-axis. So in quantum mechanics I told you that the target is considered as a region of some potential, and the incident particle is considered a wave function. So before scattering, the incident particle was far away from the target or the potential region, so it was a free particle. So this mu here is or m1 is a free particle. It is a free particle, and its wave function, let's suppose I represent this wave function by phi I, which is phi incident, and this is actually a e to the power exponential e to the power I k naught r, as where k naught is the wave vector of the incident particle. So when this incident wave collides or interacts with the target potential, an outgoing scattered wave is a spherically symmetric. So here the incident wave was plane wave, and the scattered wave is spherical wave now. Clear? So here we are calculating the scattered wave here in this region through this solid angle. Its surface area is dA, which is r square d omega. at a distance r. So here out of this potential region, the particle of the incident beam, the particles of the incident beam are like free particles, and they are traveling toward the z-axis, and they behave as a free particle. And the incident wave function is a plane wave, and that is phi incident is equal to a e to the power I k naught dot r, where this k naught is the wave vector associated with the incident particle. Here a is the normalization factor. Thus the particles of the incident beam are independent of each other. They move like a pre-particle which has some momentum. Let's suppose that is p is equal to h cut k naught. And when the incident wave collides or interacts with the target through this potential, an outgoing scattered wave that is isotropic, that is symmetrically spherical wave. So if the scattering is isotropic, so what is isotropic and anisotropic? In case of isotropic scattering, so that means that if the scattering is isotropic, then the outward scattered wave will be symmetrical spherical wave. So if the scattering is anisotropic, then the scattering might not be symmetrical spherical wave. That will be asymmetrical spherical. So in that case the outward scattered wave would be like in this form. So that might be not a symmetrical spherical wave. So we have assumed that the scattering is isotropic scattering. So in that case, the outward scatter wave will be symmetrical spherical wave, and that scattered wave, that the outward scattered wave in case of isotropic scattering, that has the form which is phi. If we represent that wave function, the scattered wave function, by phi scattered, which will be of the form a, so that will be f of theta phi e power I k r divided by r. So it has this incident plane. You see that here it was a plane wave, and here we see that the scattered wave is a spherical wave, and it has the form of e power I k r divided by r, and this k is the wave vector of the scattered wave after scattering, and it has r in the denominator. So this is because for the normalization factor, that is normalized. So we talk that if the scattering is isotropic scattering, so in that case the outward scattered wave will be of the form of e power I k dot r divided by r. So in case of isotropic scattering, the outward scattered wave will be of the form e power I k dot r divided by r. In that case, the amplitude of the scattered wave is independent of the theta and phi, and if the scattering is not isotropic scattering, in that case the amplitude is depends on the theta and phi. So here we have written the amplitude of the scattered wave as well. Now here in this direction, some of the waves arriving in this region, so some of the incident wave are scattered in this direction and some might be not scattered and they are unaffected by the potential region and they are approaching to the right along the z direction. So the outward scattered wave, the total wave here in this region will be the superposition of both the incident wave and the scattered wave. Here in this equation, this f of theta represent the amplitude of the spherical scattered wave, and this k represents the wave vector in the direction of theta and phi. Initially the wave vector of the incident wave was along the z-axis, and after scattering in the direction of theta and phi, the scattered wave vector, the wave vector of the scattered wave is in this direction. So after scattering has taken place, as you can see in this figure, the total wave function, after scattering has taken place, the total wave function consists of a superposition of the incident plane wave and scattered wave. That means that this total wave function here in this region is actually the superposition of the incident wave and the scattered wave. So the incident wave was a exponential I k naught r plus a f of theta and phi, which is the amplitude of the scattered wave, and e power I k r, sorry, k, this is k, or r, or we can write it in this form as a e power I k naught r plus f of theta phi e power I k r over r. So this is the total wave function after scattering, which is the superposition of the incident wave function and the scattered wave. Here a is the normalization factor and it doesn't affect the cross section. In the next in the coming lecture, we are actually going to calculate the differential cross section, which is d sigma upon d omega. This will be our job to calculate. This is the differential cross section in terms of the f of theta and phi, which is, it means that we are going to calculate the differential cross section uh, using the amplitude of the scattered wave. So the differential cross section is independent of A, and so we can keep this normalization factor equal to unity. So in the coming lectures throughout the whole chapter, so here A will be equal to 1. Thank you very much.